So we have a Hooke's law question here. We've got a light elastic string. Its natural length is 8L. We've been given a modulus of elasticity, which is kmg. And it's attached to the ends like this. Then they put a pebble in the midpoint, and it's in equilibrium in this system. So what's happened is the string is stretched, so we're going to have tension in the string, and these tensions are going to be equal. So there we go. So the first bit is we're going to find K. So the system is in equilibrium. So if we resolve vertically, we can see we've got, first we're going to have to define an angle here. So I'm going to call that angle theta. So in the upwards direction, I've got two lots of tension cos theta, and acting downwards, I've just got the mass pebble times gravity, so its weight is mg. Okay, now we're going to use Hooke's law, which says that tension is lambda times the extension over L. So in this case, our modulus of elasticity is kmg. Our extension, so we can have a look. So if I have a look at one side of the triangle, it was in the midpoint, so that's 4L. That's 3L, which makes this side 5L. So for one of our tensions, doesn't mean we deal with one or both, we just want the ratio. So say I just look at this triangle, I've got natural length here, and this side tells us that the extension is L, so the ratio is L over 4L. You could also use that with having 2L as the extension, natural length 8L is going to give you exactly the same answer. Right, so we can put all these things together. So I've got 2 times kmg, the L's are going to cancel, so over 4, times, now I can use my triangle again to find cos theta. So this is theta, so cos is going to be 3/5 equals mg, and then all I need to do is simplify this. So this is going to give me 3 over 10. mg is going to cancel, k equals 1, so I'm going to get k equals 10 over 3 as required. Always worth just putting a kind of mini conclusion there. Okay, so we found k, so now we know our modulus of elasticity. And the pebble is going to be pulled downwards from equilibrium until we've got the total length of the string is now 40 over 3L, and they're going to release the pebble. And we want to find its acceleration the instant it is released. And we might need to have a new diagram to think about what's happened now. So we've got our points here, so point A and point B, and they are still a distance of 8L apart. Now it's pulled down until the total length of the string is 40 over 3L. So that means one side is going to be 20 over 3L now. If I look at my triangle again, so obviously this side is going to be 4L, I can work out that this side is 16 over 3L. I'm going to have a new angle here, because angles are going to be potentially quite useful here. And as I'm going to do some resolving, I can work out, for example, so cos alpha is going to be 16 over 3 divided by 20 over 3, which is going to be 4/5. Okay, so what's happening now is my string is no longer going to be in equilibrium. So we have the same situation. I'm going to have tension acting in an upwards direction, and I'm going to have the weight acting in a downwards direction. Just move that out of the way. Okay, so we're going to resolve vertically again, but now we're not in equilibrium, so we're going to have to use the fact that force is mass times acceleration. So in the upward force, I've got 2 lots of the tension cos alpha acting down. I've got the weight, and that's going to be mass times acceleration. Now I want to find the tension again. Okay, so we're using Hooke's law again. So tension is lambda x over L. So we now know that lambda is 3/10 mg. So if I just look at one side of the triangle here, okay, I've got natural length 4L, and now this side was 20 over 3L, so the extension is 20 over 3L minus 4L, which gives us 8 over 3L. So my extension is 8 over 3L, and my natural length for that half of the string is 4L, and if you simplify that, you'll get 20 over 9 mg. So now I know my tension, so 2 lots of tension times cos alpha, which we discovered was 4/5, minus the weight is going to give us mass times acceleration. You can see mass is going to cancel, you can rearrange, and you can get the acceleration is 23 over 9 g, which, if you write to 2 significant figures, is 25 meters per second. Okay, so we had our string, and now we get to part C, and they're saying, so we've pulled the string down, we've released it, okay, and this pebble is now travelling upwards, and it's going to cross the line AB, and we want to find its speed when it crosses the line AB. Okay, it is not constant acceleration. The acceleration is going to be changing. We've got the tension in the string, pulling it up. We've got the weight acting against it. So we need to use energy instead, so conservation of energy, in order to solve this problem. Okay? Right, so let's have a look at our situation. So we've got at the start, and we've got when it crosses the line AB, it's kind of the end of our motion, and we need to consider elastic potential energy, gravitational potential energy, and kinetic energy, and there's going to be no extra work done to consider. We're not acting against friction or anything. So what have we got? So at the start, we've got the elastic potential energy. So elastic potential energy, when we're dealing with tension in strings, is lambda x squared over 2L. So our lambda is 10 over 3 mg, our extension over 2L, and we'll replace 2L here, we mean the natural length, and we'll replace that in a second. At the end, when it crosses AB, well, AB is 8L apart, which is the natural length of the string. So there's going to be 0 tension at the end. We're going to set gravitational potential energy to be 0 at the start. Okay. Then we need to have a look, and so remember from the previous one we worked out that if we looked at our triangle, that's 4L, this was 20 over 3L, oops, times L on the bottom of the fraction there. This side of the triangle you work out using Pythagoras is 16 over 3L. So our gravitational potential energy is mg, and the height we're going to move is 16/3L. Now at the start, we're starting from rest, so there's no kinetic energy, and at the end, we're going to have a half mv squared, where v is what we're trying to find. So then we can use conservation of energy. So our elastic potential energy at the start must equal our gravitational potential plus our kinetic at the end. And we can put in all our numbers. So elastic potential energy is 10.3 mg. So our extension in our string, so it was extended to 40/3L, and its initial natural length was 8L. So that's going to give us our extension. Remember, we need to square that. And then the natural length was 8L, and that's going to be equal to our mg times 16/3L plus a half mv squared. You then need to do a bit of work expanding and rearranging, and you can rearrange that and you can get v to be the square root of 32GL/27, which admittedly doesn't look very nice, but that is the correct answer. Make sure you don't miss out the square root here, because remember you'll get from v squared square root, and some people, and it is square rooted over the g and the l as well. A few people only square rooted 32/27, and then you've ended up with the wrong answer. The final part of this question about our elastic string was part D, which said to consider the model suggests a reason other than air resistance, because that's one that we quite commonly would put in as a modelling assumption, why the model and the experiment give different values, because what they have done is in their experiment here, they've put the natural length of the string was 2 meters, and they found the speed of p at the instant it crossed the line was 1.5 meters per second. Now if you actually work this out, okay, so they've said the natural length was 2 meters, which in our model is equivalent to 8L, so that gives us L is 0.25. And if you put L as 0.25 into our expression for V, you get that V is 1.70. So the experiment has come out lower than our model. So reasons why. Now the mark scheme helpfully says any sensible reason in context. So here is also some of its suggestions of what a sensible reason is. So we didn't take into account the fact the pebble has dimensions. So are we measuring there as when it crosses AB, or when it's halfway, or when it's completely crossed AB? So we could be measuring at the wrong point. We've also got to attach the pebble to the string. Okay. So that could use some of it up, and it also depends how accurate our measuring equipment was. So there's some sensible ones that suggested. There is anything else that a person mocking your scripts or your teacher considered sensible would also be allowed.